welcome back. This is Mr. Hassan's Maths channel, and I'm now going to answer question number 7 from the October-November 2005 Pure Mathematics P3 paper from the Cambridge 9709 syllabus. And this question is also question 2 for my end of topic worksheet number 14 on complex numbers from my P3 collection. And this question here is about this equation 2x cubed plus x squared plus 25 equals 0. And we're told it has one real root and two complex roots. So we got to verify that 1 plus 2i is one of the complex roots. So what we know is that if you know that some particular value is a root of a function, then when you substitute that value into the function, what should come out is 0. That's like the factor theorem. So that same would apply here. So let's say let's call the function f of x. Let's call this 2x cubed plus x squared plus 25. So we're going to find now what happens when we substitute the root, which is 1 plus 2i, into this function. So you'll have 2 times, and you have 1 plus 2i cubed, plus, and you have 1 plus 2i squared plus 25. Now if this comes out as 0, then we know this is a root. So let's see what happens. It should come out as 0, because we know that it's a root, tells us, verify. So here we're going to do 2 times, and we're going to expand this bracket here. Now when I expand this bracket, I could do it in 2 ways. I could write the square of this number. So let me just write this first. I could square this, which would be 1 plus 2 times 1 times 2, which is 4i, plus you square the last term, you're going to get 2i all squared, which is 4i squared, and you got plus 25. So I could take this part here and just multiply it by 1 plus 2i, and expand it over here. I can do that. That's one way of doing it. But we can also use a binomial expansion, which is basically where you have your coefficient, then you have your first term and your second term. The coefficient here, it's going to be basically 1, 3, 3, 1. As we know from Pascal's triangle, for cubes it would be 1, and then 3, and then 3, and then 1. So let's do it that way. So we have 1 times, let's say we start with this as the highest power, this is the lowest power. So it'll be 1 times 1, which is going to be 1, right? Because that would be 2i to the power of 0. Plus, then you have 3 times, and you're going to have, if you start with this as the lowest power, it's going to be 1. So that's always going to be 1 anyway, so you don't have to worry about this. But the 2i is now going to be to the power of 1. Plus, and you're going to have another 3, because it's 1, 3, 3, 1. And this will be 2i to the power of 2. And then you'll have 2i to the power of 3. So that's like a quick way of doing the expansion using the binomial theorem. Okay, so that's like the NCR method. Okay, so now we have, that's what we learned in P1. So now we have here 2. And we have, let's just simplify this. You have 1 plus 6i plus, now be careful here. A lot of people would multiply this and put this 4i squared. No, but this is, I would always suggest you square this first in case you make that mistake. So that's 4i squared. Then that will be times 3 plus, and 2i all cubed is 8i cubed. Close the bracket for this 2 times all of that plus, and you have 1 plus, well, let's just simplify. 1 plus 25 is 26, right? 1 plus 25, you got 26 plus 4i squared. Let's leave it like that for now. Now we can expand this. So you have 2 times 1, which is 2, 2 times 6i, which is 12i, and then we got plus 2 times 12i squared, which is 24i squared, plus 2 times 8, which is 16i cubed. So here I had 2 times, that's 12, that's 24. Plus, and you got 26 plus 4i squared. So let's just combine the like terms. You got 20 plus 26, which is 28. You got 12i plus 4i, which is 16i, and you got 24i squared plus, and you got 16i cubed. Okay, 24 plus 4 is 28. Let's do that first. Let's do the like terms. You got 24i squared and 4i squared, which is 28i squared, plus, and you got 16i cubed at the end. That's 16i cubed. So we have now combined the like terms: the 2 with the 26, the 12i with the 4i, the 24i squared with the 4i squared. Okay. So now what we know here is that I squared is equal to minus 1 by definition, right? Because we know that the square root of minus 1 is equal to I. So I squared is equal to minus 1. So what I can do is I can say this is 28 plus 16i plus 28 times minus 1 plus 16 times I times minus 1, because it's like I times I squared. Alright, so we end up here with 28 minus 28 plus 16i minus 16i. As we can see, that becomes 0. So we should write a little statement as, when we put inside the function 1 plus 2i, as f1 plus 2i is equal to 0, therefore x equals 1 plus 2i is a root of the equation. We call the equation f of x equals 0. Okay, so there we have our answer. We should write a little justification, but you see that when you put the root inside this function, if you put this number inside the function, if it comes out 0, we know that it's a root. Okay, then part 2, it says write down the other complex roots. Well, we know that roots come in conjugate pairs, so we can say that the conjugate pair for this root is going to be 1 minus 2i. Oops, I went to the pen there. It's going to be 1 minus 2i. 1 minus 2i is the other root. So it just says write down, that's just looking for that, and that's fine. That's the conjugate root of the other root. So it's just the same thing with the opposite sign in between them. Complex roots always come in conjugate pairs. Okay, there's always pairs of roots. Alright, so there's part 1 and part 2 done, and part 3 now. It says sketch an Argand diagram showing the point representing the complex number 1 plus 2i. Then show on the same diagram the set of points representing the complex numbers z which satisfy this equation. So this is to do with loci. So basically what it is you must express them in the form of z minus z1. Okay, so we have z minus, we can say the modulus of z minus z1 is equal to the modulus of z minus, let's call it z2. Okay, the modulus of z minus z2. So basically what it's saying is that the complex, this particular point z is such that it should always be the same distance between the points z1 and z2. The difference between z and z1 in terms of its magnitude should always be the same as the distance between z and z2. So it's describing basically the points which are the perpendicular bisector of 2 points. Okay, so for example, if this is z1 and this is z2, then z has to always be the same distance from both of them. So it has to be the perpendicular bisector. So if we think about what z1 is, in this case z1 is going to be 0, 0. Alright, this is going to be, if you do z minus, you say 0 plus 0i. Okay, that's going to be, we can say z1 is going to be 0, so that's the point 0, 0. Alright, and z2, what we have to do is you have to rewrite this in the form, this is supposed to be modulus, sorry. Okay, you have modulus of z minus, now what we have to put in this bracket is such that when I expand this I get this, so I have to have a 1 here, so it becomes minus 1. I have to have a plus 2i here, so it becomes plus 2i. So z2 is equal to 1 plus 2i, which is the point that we have to plot here. Okay, so we know that z, okay, or the points that represents the complex number z must be the perpendicular bisector between these 2 points. Okay, so between the point, basically this point is represented on the complex plane by 1 and 2. So if I draw the Argand diagram, here, you have your complex plane and you have your real plane. Okay, you have the point z1, which is origin, and you have the point z2, which is 1, 2. So let's say that's 1 and let's say that's 2 up here. It's a bit far, let me put it a bit closer. 1 and 2. It's just a sketch, it doesn't have to be 100% accurate. This is the real axis, this is the imaginary axis, which is z, okay, which is which is imaginary, just call it imaginary axis. Okay, the imaginary part of z, and this is the real part of z. Okay, this is the imaginary component of z, this is the real part of z. Okay, so now, so we have the point 1, 2, which will be over here. Okay, so this is the point z, well, I'm going to call it z2. Okay, z2. So this is the answer to part 1. This is the point z2. Okay, this is I plus 1 plus 2i, which is 1 plus 2i. 1 in the real part, 2 in the imaginary part. So the perpendicular bisector of these two is going to be the line that we have to draw. So we have to draw a line which goes halfway through these two. Okay, and it cuts in half the distance between them, and it's perpendicular to them. It's basically perpendicular to the line joining them. So it's the perpendicular bisector of Z1, Z2. Okay, so if we wanted to draw it kind of accurately, or show, for example, where it passes through the axis, we could find this equation. I don't think that's really necessary, but let's just do it anyway. So this is like the point 1, 2, and this is 0, 0. So we can say the midpoint of these 2 points is going to be basically a half, and on the y-axis is going to be 1. So it's be a half and 1. So a half and 1 would be the midpoint. Okay, so it passes through that point, and the gradient of this line, this between these two is going to be basically 2 minus. It's going to be basically 2, right? So the gradient of our line is going to be minus a half. The gradient of this is minus a half. Okay, so we can say that its equation will be, we can say y minus y1 equals m times x minus x1. So we say y minus 1 equals the gradient, which is minus a half, times x minus a half. Okay, so you have y minus 1 equals minus a half plus a quarter. So you can say y equals minus a half x, sorry. It's going to be minus a half x, and it's going to be minus plus a quarter, and plus 1, which is going to be plus 5 over 4. Okay, so that's going to be the point 5 over 4. And this is when y is going to be 0. When y is going to be 0, you'll have minus a half x equals minus 5 over 4, so it'll be plus 5 over 4. So we can say here that x is going to be 10 over 4, 10 over 4, which is going to be 2.5. So this is going to be 2.5. That's 5. That's 1.25. So here we have, you can put 1.25 here if you want. There we have the line that is a perpendicular bisector of the line joining these two. That is a loci of z. So z can be anywhere along this line here. Okay, so that's how we show on the same diagram the set of points representing the complex number. If you want to, just make it clear that you are drawing the perpendicular bisector. You join those 2 points together, and you can write this as, show this as a perpendicular bisector. Okay, so in this question here, we are not really required to find the equation. Okay, so that's just a bit extra. As long as you show that the line that we're drawing is going through the midpoint, so you should mark that this is the midpoint. Maybe showing that this is midpoint, making it half 1 is a good idea, and showing that, you know, it's the perpendicular, that there's perpendicular to the line joining these 2 points, and it meets that right angle. So you showing these things might be something which would be helpful. Okay, that would be helpful. Finding the equation is not really necessary in this question unless they ask you to do it. I've just done that as a little, you know, demonstration in case they do ask in any particular question. As long as you mark the point 1, 2 and the point 0, 0, okay, and you mark, you know, you draw this line such that it looks like it's perpendicular to the line joining these two and cuts it in the middle, maybe marking the midpoint and showing that these are perpendicular with the right angle and the 2 lines to show that it's bisected. That would be enough for you to get the full marks for this question. So that completes this question from this paper, October, November 2025. This is question number, what was it? 7. I hope that was clear. Other questions from this paper can be found in the playlist that will appear in the top right of the screen at the end of the video. Other questions from this end of topic worksheet, number 14, in the playlist over here. Questions from complex numbers in general from my Cambridge collection can be found in the playlist in this section here, and you can subscribe to my channel by clicking on this link. Thank you for watching, and see you soon.